Good morning and welcome to the series of lectures on acid-base balance. The first of it is the basics or the part 1. So a lot of confusion about what is what. Sometimes anions are called bases, sometimes called acids. So much of confusion. But we should know the definition of what is what. Let's know the definition of what is an acid like. Acid is an hydrogen ion donor. This is what we should know. Acid is an hydrogen ion donor. For example, acid if you put in solution, it will give hydrogen ion. It's an hydrogen ion donor plus a base. Now you see carbonic acid, H plus plus, this is a base. Bicarbonate is a base. See here, phosphate, hydrogen plus phosphate. This is dihydrogen phosphate, trihydrogen phosphate. Acid is a donor. That is what is an acid. A base is a hydrogen acceptor. Now you see this will accept this and become this. That is what is a base. An acid is a hydrogen ion donor. A base is a hydrogen ion acceptor. Now these are bases. Now what is an alkali? An alkali produces hydroxyl ions in solution. This is an alkali. Alkali gives sodium plus hydroxyl ion. Alkali is strong, more hydroxyl ions in solution, and more hydrogen ions in solution is a strong acid. Now we should understand the differences between acid, base, and alkali. Acid is a hydrogen ion donor. Base is a hydrogen ion acceptor. Alkali is a hydroxyl ion donor. This is what is the big difference between these three things. In 1909, this fellow Sorensen found out enzyme activity changes with minute or minimal changes. So many enzymes are there in the body. If the pH is 7.4, it functions like 1. Now, if the pH is 7.3, it functions differently. This is what was invented by Sorensen. Now we will go 0.001 mole per liter of hydrogen ion. How to write this? 10 to the power of minus 4. Something like that. 10 to the power of minus 6. Write like this, take the power and make it positive 4. Negative logarithm of hydrogen ion concentration. This is what is called the pH. We cannot go on writing like 10 to the power of minus 10, 10 to the power of minus 10, 7, something like that. So the hydrogen ion concentration is 10 to the power of minus 7 moles per liter. You cannot write like this. So what we do is we create into a negative logarithm and say pH. So if the hydrogen ion concentration goes up, the pH will decrease because it's a negative logarithm. Okay, a solution of pH of 4 has 10 times the hydrogen ion concentration than the pH of 5. It is never linear. Now you see 4 is the pH. Now you take out the hydrogen ions. It becomes 5. Now again come back. Hydrogen ions. This is not linear if it transfers us from 4 to 5 and then 5 to 6. This is not linear. The same amount of hydrogen ions is not there. So it's a different thing. That is what is called a non-linear relationship between hydrogen ion concentration and pH. What is the neutral pH? Water dissociates into equal amounts of hydrogen and hydroxyl ions. This is in chemistry is 10 power minus 14. So 10 power minus 7 equal. 10 power minus 7, 10 power minus 7. So the neutral pH is minus 7 or a negative logarithm. It becomes 7. Acids have more hydrogen ions and less pH than 7. Which is strong, 0.001 or 0.01. Alkali means more than 7. Now we should fundamentally understand that in chemistry, blood is alkaline because neutral pH is 7. Blood is 7.4. It's faintly or mildly alkaline. In pH of 7, that is neutral pH, no acidosis as far as chemistry is concerned, but acidosis clinically is oxygenation of hemoglobin is impaired. Now we go pH is equal to pKa of log K plus HA. This is what we have been told. That's Anderson's also. If the pK is 3.9, then the acid is a stronger acid than the pK of 6.1. At any given pH, lactic acid will be more dissociated and produces more hydrogen ions. That is what is called a stronger acid in solution. Now you know what is a stronger acid. At a given pH, dissociation into hydrogen ion is more with lactic acid than carbonic acid. So lactic acid is a stronger acid. Carbonic acid is a weaker acid. This is what we should clearly understand. Lactic acid is a stronger acid because the hydrogen ion dissociation production is more at a given pH. Now you see this is the bleach from alkali to acid. Replenished continuously. Our life is acetogenic. It constantly produces non-volatile and volatile acids. Volatile means that it becomes gas that can be excreted to the lungs. So carbonic acid as carbon dioxide through the lungs. These are all non-volatile acids. They need kidneys to excrete. These are non-volatile. They cannot become or they cannot get converted into carbon dioxide to get excreted through the lungs. Lactate has to be excreted through the kidneys. Now you see 40. It becomes 50, 7.3. Now it becomes here, this is what is called the non-linear relationship. 50 to 60, it doesn't become 7.3 to 7.2. Non-linear progression of hydrogen ion concentration and pH. This is the hydrogen ion concentration in 40 nanoequivalents per liter or 10 to the power of -7, or it becomes the pH is 7.3 or 7. Now we have understood what is an acid, what is a base, what is an alkali, what is a strong acid, and what is a weak acid. Now we go what is buffer. Buffer means a person is normal. Buffering. Buffering means if there is some fight is there, he compromises. He buffers the things. Something like that. Doesn't make big change if somebody enters. If somebody enters into a fight or something like that, not big changes are there. That is what is called a buffer. Now you have a solution. Okay. Now this is a buffer. Now you add hydrochloric acid in this. It's a buffer. The pH doesn't change much. This is what is a buffer solution. Water is great. Sodium hydroxide plus water. Alterations in buffer balance leads to significant concentration problems in cardiovascular systems. The body's chemical buffer system consists of individual buffers. Carbonic acid, bicarbonate buffer. This is the common. Phosphate, protein. This is in ECF. Extracellular fluid 3. Carbonic acid, bicarbonate. Phosphate, protein. These three things are there in ECF. Now we will go each. Now you have carbonic acid and bicarbonate buffer. Now you are adding a strong alkali into this buffer. What happens is it combines with this and produces a weak alkali. And slowly it becomes strong acid. If you add strong acid, what happens? It's a normal thing. Hydrogen ion is added. This combines with this bicarb and then becomes a weak acid. So this is what is called a buffer. If you add a strong acid, it will combine with it to become a weak acid. If you add a strong alkali, it will combine with this to become a weak alkali. So this bicarbonate carbonic acid combination is a buffer. It's a buffer. So this is what is called a log of HCO3 plus H3CO3. If you combine this, this is a pH of 7.4, the normal. Now we have know what is a most important thing. Carbonic acid bicarbonate buffer. If you add acid to it, it will add like that and become a weak acid of carbonic acid. If you add alkali to it, it will become weak alkali. So that is how it acts. Now we will go to phosphate buffer system. This is disodium hydrogen phosphate and sodium dihydrogen phosphate. There is a weak acid. This is a weak base. Now you add hydrochloric acid. the strong acid, it becomes a weak acid. This happens in kidney tubules and RBCs. Now you see, you had a strong alkali, it become a weak. So disodium hydrogen phosphate and sodium dihydrogen phosphate. This is a weak acid and alkali. All this becomes a phosphate buffer system. What is a protein buffer system in blood plasma and cells? Nearly all proteins can function as buffers. Proteins are made up of amino acids. They contain positively charged amino groups and negatively charged carboxyl groups. So negatively charged carboxyl groups la hydrogen ion may get attached. Positively charged amino groups la NaOH, OH can get attached. So these may act to produce weak acids or weak buffers. So that is what is called a protein buffer system. Now we have clearly understood what is a buffer system in ECF. Number one is carbonic acid bicarbonate. Number two is phosphate buffer system. Number three is protein buffer system. Now you see, hemoglobin occurs within the red cells. There is a hemoglobin. Now if you add HCl, automatically it becomes converted into a weak acid. Hemoglobin is a protein. This is how it acts. What is the contribution? Bicarbonate, carbonic acid is the main thing. Hemoglobin is like this, plasma protein and phosphate. This is how in whole blood the contribution is there. Can we repeat or can we go ahead? There's so much of confusion is there. We will again repeat. Now we have told about what is being done in the ECF. Now we will go to respiratory regulation. Now there is a plasma pH is increased. Patient is become acidotic. 7.4 to 7. Peripheral chemoreceptors are stimulated. Ventilation is increased. PCO2 is decreased. The pH increases. There is a negative feedback. CNS receptors. This is how respiratory regulation acts. It may also be having a central chemoreceptors. So chemoreceptors sense the pH, sense this hydrogen ion concentration, goes again because sometimes the peripheral chemoreceptors may be more sensitive to hypoxia, while central chemoreceptors may be more sensitive to carbon dioxide concentration. This is a relative thing, but whatever it is, something happens, ventilation is increased, carbon dioxide is thrown out, and then your pH comes back to normal. Unless you understand these things, interpretation of ABGs next time is going to be difficult. So because if you see a normal pH, the patient may be an acidotic patient. Acidosis is a progress of going to acid, and a respiratory compromise is there, then the pH will be normal. You may think that the patient is normal. Unless we have understood all these things, the next time ABG interpretation classes will be difficult. Doubling the respiratory rate for less than a minute, removing extra. The situation is common if you do exercise. So this helps to keep you developing acidosis. Medullary chemoreceptors. Carbon dioxide is more permeable ventilation. This is what I told. Peripheral carotid receptors, they may be more sensitive to hypoxia cells. Up to 7 hyperstimulation, and if there is pH is 7.2, it is okay. 7.1, okay. It becomes 6.2, nothing, complete depression. Now if you give massive doses of alkali, depression, again the same thing. PCO2 will increase and the patient will go bad. Now we have concentrated on ECF, on bicarbonate, carbonate, proteins, and phosphates. Now we have also told about the respiratory regulations. Now we will go to renal regulation. The kidneys control acid base by excreting either acidic or basic. Normally it will excrete an urine with a pH of around 6.8 or 7. If you give acid, it will excrete by 6.2. If you give alkali, it will excrete by 7.2. This is what happens. Renal regulation. Three mechanisms are there: resorption of bicarb, acidification of buffer salts, and secretion of ammonia. Now I will show to this. Now we have carbon dioxide is coming in, carbonic acid is formed, and this H plus goes out into the tubular lumen and automatically it gets excreted. Now carbon dioxide is coming in from the tissues, and it gets from the tissues, renal interstitial fluid. Carbon dioxide is coming, and this gets converted, and this gets excreted. For other things, sodium comes in, sodium goes out, potassium comes in, all these things happens. But what happens is carbon dioxide comes in, hydrogen ion is excreted, and normally carbon dioxide is absorbed into the interstitial tissues. Okay, bicarb. Bicarb is absorbed. Carbon dioxide comes, bicarb is absorbed, hydrogen is excreted. It's a simple renal acidic regulation of body pH. Acidification of buffer salts. See here, carbon dioxide, carbon S, this hydrogen goes out, S. Here you can see this also acts. Sodium phosphate and sodium phosphate negativity is there. This also may act. Acidification of buffer salts. Buffering by ammonia also occurs. NH3 will become NH4 plus and gets excreted. So what are the things which happens? Normally carbon dioxide, bicarbonate S. Another is phosphate. Another is ammonia. These are all the three things which happens in renal things to get this thing excreted. Urine pH may vary. So what is normal? Interrelation of buffers, metabolic changes, but not in a linear fashion. We expect the bicarb to decrease, but does this happen? Changes in are dependent on also respiratory acid base variations. This will come again in ABG analysis. ECF, yes, there are three mechanisms which I have told. ECF, respiratory, kidneys. ECF mechanisms are instantaneous. Respiratory mechanisms may take a few hours or a few minutes or something like that. Kidneys may take hours to days, but mechanisms by the kidneys are permanent.